Welcome everybody. I'm very happy to be standing here today following the very exciting announcement that we have now decided to team up with Nexa. I have taken the liberty of preparing a few slides for you guys so that you'll have the opportunity to have a closer look at what freeform injection molding is and what freeform injection molding does. Okay. So starting off with the basics about Addifab, we are a company that was founded about 7 years ago. We have pioneered this noble art of 3D printed tooling, which we call freeform injection molding. And to date, we have managed to get freeform injection molding installed with manufacturers in the US, several countries in the European Union, as well as Japan and Taiwan. To support the US audience, we have also established a sales/demo office in the Silicon Valley region, where we will shortly be demonstrating also Nexa equipment combined with injection molding. If we look at freeform injection molding from the process point of view, what we have developed is a perfect integration between the 3D printing and the injection molding. The objective has been to ensure that product developers do not have to compromise between the design freedom of the short lead times, low startup costs offered by 3D printing, and the versatility and scalability that is the domain of injection molding. So we have developed some software that will help users automate mold design and mold preparation. We have developed some printers and other hardware that is also available. Of course, with the Nexa offerings, we are dramatically expanding what we can do in terms of size, in terms of productivity, but I'll come back to that a little later. Following the 3D printing, we will need to clean the printed tools. That's pretty standard. For any DLP or SLA or LCD printing, resin will have to be removed from the surface of the tooling. And we will also need to post-cure the parts to make them ready for injection molding. Injection molding happens using standard injection molding equipment like the baby plastic setting over here, which was to take place part in the live demo, but I guess I'll have to use pre-taped recording since I cannot hold my laptop and manage the machine at the same time. And over here we have a 50-ton Kraus Maffei, which is essential for molding of the larger objects that are enabled by the Nexa systems. And then finally, as the key part of freeform injection molding, we have the demolding, which is where we dissolve those parts of the 3D printed tool that cannot be removed mechanically. So in short, we are providing an end-to-end tool chain that allows injection molders to prototype even the most complex injection moldable parts they can think of. So freeform injection molding, as mentioned, is about 3D printing injection mold cavities or injection mold parts for cavities. The printing principle is DLP, or with the Nexa systems, we use LCD, which allows us to create a large number of printed tools in the same process. When Addifab was working with the Addifab machines, we had the opportunity to print approximately 15 tools with the printer. Now with the Nexa, just to provide you with a little bit of insight about sizes, we can do 120 molds in the same time. And that means that the time to print one of these injection mold tool cavities is 15 seconds with the Nexa system. For injection molding, we use any standard injection mold machine. In this case, it's the baby plast with any granulate you may think of. We do peaks, we do metal, we do ceramics. The objective is to provide the injection molder with the same degree of choice that he would have with any other technology. And then following the injection, where the material is squirted into the tool, follows the demolding, which is that part which provides the injection molder with an unseen level of design freedom, since we don't have to worry about sliders or split lines or drafts or any of the complications usually associated with injection molding. So freeform injection molding is injection mold tooling, is injection molding with the key benefits offered also by 3D printing in terms of short lead times, low startup costs. And for your information, the tools we were looking at here have an average production price of a couple of euro, which means that of course your unit costs increase slightly, but compared with the price, the cost, the investment that would be needed for injection mold tooling of this complexity, a couple of euro shot is pretty trivial. So the reason why we have invented and are pioneering freeform injection molding is because when you look at product development from the injection molder's point of view, getting from the 3D printed prototypes to the injection molded products is a key challenge. And the challenge is primarily associated with investments in injection mold tooling. Of course, we would like to be able to offer a solution that spans more than just the product development. And one of the key benefits of using freeform injection molding for product development is that once you have defined your recipe for injection molding your low volume products, that recipe will follow your product throughout the life cycle, which means that you may well want to migrate to conventional steel tooling for mass manufacturing. But whenever a customer wants a customized version of your high runner product, you can simply resort to 3D printed tooling to meet the demands of that low volume manufacturer. And when you start talking about spare parts manufacturing later in the product lifecycle, you will also be happy to acknowledge that instead of stockpiling items that may have to be written off and discarded at the end of the product lifecycle, you can produce your spare parts on the demand, once again, reusing that low volume production recipe you compiled in your design phase. So for all intents and purposes, what we are delivering with freeform injection molding is the total product lifecycle management solution. And the reason we are teaming up with Nexa3D is because at Addifab, we have been dedicated to the manufacturing of small, high precision items, but we've also received a lot of requests from customers wanting bigger printers and wanting printers with a higher productivity. So what we have been focused on until basically today has been small parts up to 5 centimeters and batch sizes up to about 20. Now, with the Nexa, we can substantially increase our approach to market. We can substantially increase the number of applications we can support with freeform injection molding, and we can support a much higher level of production than we have previously been able to do. People are often asking us why we are different from conventional 3D printed tooling. We are not the first, we're not the only company in the world offering 3D printed tooling, but I think the design freedom that comes from having soluble tooling is a key part of what we offer. Another key part that we offer is the very, very extensive selection of materials that comes from not having to optimize for as many shots as possible. What you see in this image is a black part, which is made in a high performance PPA with a 30% carbon fill. This part has a weight of 70 grams. It carries more than 4.5 tons of load. And it is enabled by the solubility that is the key feature of freeform injection molding. When we look at freeform injection molding compared with conventional injection molding, one of the things that is evident from the start is that when we want to manage complex components, we can do so at a much lower price point. This is an example of a fairly complex tool, a couple of side actions, a lot of complex split lines. You could basically achieve the same functionality with a one-piece 3D printed cavity if that cavity was soluble. And that means that with freeform injection molding, especially the high complexity components become a lot easier to source in low volumes. A topic that is creeping up on the agenda in a lot of places is sustainability. And at Addifab, we've actually decided to investigate the environmental profile of freeform injection molding when held against conventional metal tooling. We carried out a life cycle analysis with Deloitte, the world-leading auditor handling the mathematics. And what we saw was a substantial reduction in CO2 emissions associated with the product development. As a matter of fact, freeform injection molding allows us to reduce carbon dioxide emissions with 75% compared with reference pilot tooling on the manufacturing, in this case, of a 4-part medical device for preclinical trials. Most of those savings come from not having to iterate in a hard tool, from not having to manufacture a hard tool, but we also see substantial savings in not having to run in a hard tool, because with freeform injection molding, you shoot once or twice, and then you're basically at the stage where you should expect to see fully molded parts. And then, of course, it's a key benefit that your lead time drops with more than 80%, and that your times to first start of tool components will also drop with more than 80%. When we look at what people have been doing with freeform injection molding, the scope of application is extremely wide. And that is also one of the key benefits that we see with this technology. Whenever you need injection molded parts, and sometimes even when injection molded parts would not normally be useful, we can probably help with freeform injection molding. Looking at a couple of examples, and I can share this presentation afterwards, so you won't have to sit here, watch the screen. But sustainable materials, recycled materials are often not available in filaments or powders. Most material manufacturers will want their materials to be injection moldable. And freeform injection molding is becoming a very, very useful gateway for these material manufacturers to get their materials into the hands of developers. In one case, the developer was a UK person wanting to do shirt buttons and recycled materials, but we've also been making prize awards for innovation contests. Conductive polymer parts may be useful if you want to start using antennas for your car or similar. In this case, we had to collaborate with Harting and Mitsubishi Chemical in order to get this unique combo to work. We've also received substantial help from Mitsubishi Chemical when doing the prosthesis for the table tennis player that is the centerpiece here. We are very proud to have been able to supply world-class athletes with tools that could actually be used at a Paralympics game to win a silver medal. But this is just a very, very specialized application of freeform injection molding for one individual. Other cases involve the combination of metal tooling and 3D printed inserts. We do micro injection molding just as well as overmolding, medical device manufacturing, parts for cars. And all these different applications are powered by that versatility of freeform injection molding, which allows us to process from the softest thermoplastic elastomers to the hardest metals on the same platform. In order to support your evaluation of freeform injection molding, Addifab has set up a manufacturing center. That's where I'm standing right now, which allows us to do the entire process from the design of tools through the printing of molds to the filling of these molds using the standard thermoplastic materials supplied by customers or that we procure ourselves. We are presently a little bit constrained. The biggest injection molder we have is a 50-ton machine, as I mentioned before, but we are looking to expand the capacity with a larger injection molder so that we can capture the full benefits of the larger molds offered by the Nexa3D systems. And then we also have a very nice on-demand manufacturing collaboration with Mitsubishi Chemical. Since they're boasting our machines in Tilt and in the US, customers may also access their capacity and capabilities for the freeform injection molding. Then as my final statement here, If you are situated in the European Union, you'd want to note down the phone number of Mr. Jan Skov, whereas Carsten Jarfeld is our head of everything in the US. He's situated in Palo Alto, whereas the Addifab headquarters are situated in Denmark. And then to very shortly recap what I've been talking about so far. Freeform injection molding is 3D printed tooling that combines the benefits from 3D printing and injection molding. By printing soluble tools, you can work with injection molded design freedoms that are unachievable with conventional injection mold tooling. And that also means that if you have to manage complex injection molded parts, freeform injection molding is probably the most useful 3D printed tool in your toolbox. For injection, we are compatible with the entire range of standard injection mold machines. We are compatible with a major part of the injection moldable materials. And that means that as a product developer, you will not have to make the usual compromises between having 3D printer short design times and low startup costs and injection mold scalability and versatility. You can actually get both using this platform. And then finally, as mentioned, the solubility is the key Addifab innovation. That is what allows us to break design barriers and to bring you a 3D printed tooling technology that is more versatile and more suitable for complex injection molding tasks than any other platform in the market. And then, since I didn't have to do the live demo, we have a few more minutes than anticipated.
Awesome. Thank you, Lasse. We have several questions coming through. What is, Max asks, what is the dimensional tolerance of the tool or the plastic part coming out of the system?
We usually expect a tolerance of plus minus 1/10 of a millimeter on the first iteration we do. Depending on the printer configuration, we can step from 75 micron down to 10 micron resolution. And that means that if we need to do finer tolerances, we will usually do a second iteration to tweak mold designs to take up any out of tolerance dimensions. And if we need to do very, very fine features, we can include either complete tools or we can include tool parts that are printed with a 10 micron resolution. The nominal precision with a 10 micron insert is plus minus 10 micron, and that should cover most requirements, at least in the injection mold prototyping domain.
Awesome. I have another question from Benjamin. How often does the chemical, so that assuming that's the dissolving chemical, need to be replaced in the demolding step? And how do you dispose of it?
Well, disposal depends on local regulations. In Denmark, we have some pretty rigorous waste management paradigms. So we treat our waste products as standardized in industrial waste. I can share the waste codes that we use in the European Union. As a rule of thumb, you should expect to have to change 1 kilo of demolding solvent per 200 grams of material you dissolve. So the saturation point is about 20%.
Another questions come from several folks about the dimensional stability of the process in terms of, I'm assuming, what's a CAD file versus finally what the plastic part comes out of. In your experience, what have you seen in terms of stability?
In terms of stability, you should expect to be within plus minus 500 to 1/10 of a millimeter when you look batch over batch. The process itself is pretty consistent, but of course, if you look at the tolerance chain with the 3D printing and the injection molding, perhaps sometimes even with the split tooling that is put together, you may see larger tolerance variations than what you would see with a conventional metal tool. The good thing about freeform injection molding is that when we detect these inconsistencies, we can usually design our way around them. And if we need particular features with ultra high precision or repeatability, we can include steel inserts into the 3D printed tool to manage the processing of specific features. These inserts are then either removed after the injection molding, or they are put into the tank with the 3D printed mold, depending on the application.
So Lasse, you've mentioned now two things in addition to dissolving the tool. So most of the presentation was about printing a tool, injecting, and then dissolving, but you mentioned split tooling and you mentioned insert tooling. So could you summarize what's all possible? So it sounds like it's more than just dissolvable tools that are possible on your technology.
That's absolutely correct, Jan. I'm carrying my laptop around, so sorry if some of this appears a little messy, but I've just been picking up an example. So what we are seeing here is one part of a tool. It's a tool that is used for the manufacturing of a dedicated cap. And in this case, we are using a middle portion, which I do not have with me presently. Then we've got an injection point here, and then we've got the cavity. The reason for this particular tool design is we want to be able to take apart as much of the tool as possible before we start demolding. Two reasons for that. First, of course, is we save time, we save solvent. Second, we get to evaluate the part a lot faster if we can take apart the tool before we start demolding. So
hey,
what
Lasse,
we always, yes?
Lasse, sorry to interrupt. People can't see you. Can you go to full screen so that folks can see you? What you're showing?
Sorry.
Yeah, awesome. And maybe can you rewind a little bit and just show that part again?
Absolutely. I'll just, can you see me on full screen now?
Yeah, go ahead.
Okay, good. Okay. Thanks, Jan. So this is the top part of a tool that is used for the manufacturing of a cap, a threaded cap. The midsection, which takes care of the inner geometry of the cap, has been taken out of this tool and it has been demolded or dissolved. And then we've got a bottom portion, in this case, with an inlet, which is also removable. And the reason why we've got this removability, this reason why we are taking the tool apart before dissolving, is because we want to save as much time as possible. We want to potentially reuse our parts, and we want to be able to evaluate what comes out of the injection mold machine before we start demolding. So quite a few of the tools we make are actually split tools that are partially taken apart before dissolving.
Awesome.
And then about the inserts.
Yeah, go ahead.
Yeah, allow me to fetch a second box. And thanks, by the way, for the great questions.
We have several more coming up.
Yeah, but don't worry, I'll be here.
We have enough time, so please ask more questions.
Yep. Okay. So this is another cap, or it's an essential part of a mold for a cap. Now, this particular cap is a spray cap, which means it has a pretty intricate inner geometry. I cannot show the cap itself for confidentiality reasons, but I can show you a couple of the tool principles. Now, we've got a mold base, and we've got a 3D printed tool part. And now I can use the combination to create a feature that would be impossible for me to do with a purely printed tool, and that is quite a lot more cost efficient to manufacture than a complex tool with side actions, sliders, and other complications. So this is a way to combine the best from conventional metal tooling and 3D printed tooling to achieve lower lead times, lower tooling costs, and parts that come out quite a lot faster than what would have otherwise been achievable.
Could you say something about how much output you get from a non-dissolvable tool? What's the best you got or an average you got? Obviously depends on the complexity, but just some indication of how many parts you got before. And why did it stop? Was it deterioration of the mold or the part or dimensional issues?
Oh, it very much depends on the materials. Of course, if we look at parts like this one, which is our reference double helix in a standard size, we get 1 shot per tool. If we look at the TPE material that this part is made of, we can do 50 or 100 shots per tool before we start to see degradation. But since the geometry requires us to dissolve, well, of course, it's a one-shot story only. When we talk about high-performance materials like PEEK or PPA or glass-filled nylon, we should also expect to get only 1 shot out of each tool. But again, it also depends on the tool design. It depends on the part design, how many shots we can expect to get out.
Awesome. 2 questions about, one is about overmolding. Can you overmold over aluminium in this tool? Have you tried that?
We have tried overmolding. One of the cases that I showed in the presentation is a case which shows a PPS body, glass-filled 40% PPS. I'll just look up the slide while I talk. And this glass-filled PPS has then been overmolded with a TPE color. So that's of course a 2-step process. We cannot do the automated rotating table style like conventional tooling does. But let me just share my screen again. What we see here is a pretty nice example with that 40% glass-filled PPS overmolded with a TPE color. And again, I'd be happy to share visuals with you if you just let us know your mail addresses, then I can send you this presentation. And I can also show you in greater detail what this particular component looks like.
Very good. So there was a chat question which I answered about the hottest thermoplastic you could take in. Maybe you could answer it more technically. What's the maximum temperature thermoplastic material? I'm assuming it's some kind of a filled PPA, PPS, or something like that, which you have shot into a mold of yours. Can you throw more light on the conditions? And,
we certainly can.
And the second sub part to that is then the materials, the resin, it's not the same resin, right? So I'm assuming there are different mold. So for a hot material, is it the same blue material you showed, or is it a different formula? So could you please throw light on that?
Absolutely. So the holy grail in every manufacturing process that I've heard about is PEEK, because it's insanely hot when injected. And we've done standard PEEK, we've done carbon field PEEK. I wouldn't say since the beginning, but we were pretty quickly faced with demand on PEEK parts from several manufacturers. Now, PEEK is a pretty special material. It's crystalline, which means that it has to cool down at a specific rate. And what we see with the PEEK is that for very thin walled components, we are not able to achieve the crystallinity that you can achieve with a heated metal tool. Once walls start getting thicker, it actually becomes a benefit that the mold is a good insulator, because it means that the PEEK cools down slowly. But if we have thin-walled parts, we need to post-anneal the PEEK. It's injected at between 380 and 415 C, which means it's one of the hottest materials we've got. We've also tried molding SAMAC at 420, where we cast it directly into the tools. That's also possible. And then not as hot, but it stays hot for longer. We use freeform injection molding also for metal injection molding, where feedstocks have a much higher thermal capacity and where thermal stress on the tools is sometimes even bigger than on the PEEK molding. Regarding the different resins we have, we've actually cut things a little bit differently. We have a resin which combines UV curing with thermal curing, and that one was developed primarily for medical device applications where we need to ensure 100% curing of the molded material, the printed material. But that one is also very, very thermally stable, and we recommend that for high temperature applications.
Awesome. There's a question. is there any special consideration? If somebody has a Nexa NXE400 printer today, is there anything special they need to do to run one of those resins to produce one of those blue molds you showed?
We are still optimizing parameters, but what has impressed us the most about the Nexa systems was the plug and play like nature of running in the resins that we've developed. There seems to be a very, very high native compatibility between the Addifab resins and the Nexa machines. And we haven't really come across any problems with curing the material. It's important for me to mention that the Addifab experience with larger 3D printed tools is pretty minimal at the present stage. We have been focusing, as I mentioned before, primarily on small precision parts. But what we have seen when stepping up the mold size is that as long as the mold is properly supported by a metal frame, there seems to be no particular challenges associated with increased size. Of course, taking apart the tools before demolding essential parts becomes more important, because if you have a block of material that's 4 kg, it'll take a while to demold. So mold design guidelines may have to be updated a little, but printing and injecting into these larger tools does not seem to be a challenge in itself.
So 2 questions from that, which are also in the chat. Maybe you can show the largest mold you printed on the NXE and comment about its size, dimension, and so on, and if you have shot any plastic in it. And then a sub question is, say something about the mold design process, the software. I think that's a very important topic you should elaborate on, because that's really your secret sauce to put all this thing together.
Yep. Starting with the molds, the largest one we have printed has been sent to the US. So this is a mid-size. You can fit 3 of those onto an Nexa build plane. But already here, and well, okay, that's just for reference. This is our standard. I'm trying to demonstrate the difference. This is our standard double helix, which some of you may have come across at trade shows. So this one has a weight of about 1 kilo. We do not have an injection mold machine at Addifab that is big enough to fill these. So for that particular challenge, we are collaborating with Mitsubishi Chemical in Tilt, because they have bigger molders. We need to get a mold frame made for this particular part, so getting it filled will take some weeks. But as you can see from the mold makeup, there is no difference between this one and this one, apart, of course, from the size. Now, when we talk about mold design and the mold generator, that's something that we are actually planning to do a separate webinar about. The mold generator was devised primarily for small unitary mold constructions. And we would like to be able to update the mold generator so that it can also properly address the larger molds before we start introducing a version that is Nexa compatible. But what we can already see now is that for many companies, for many individuals starting out with freeform injection molding, it's a huge benefit to be able to simply load a component into the system and then have the system automatically compile a mold that can then be fitted out with injection points and vents, depending on user preferences. Saves a lot of time, saves a lot of errors. And we're already using the software, of course, in our own manufacturing center to drive down time consumption.
So you said that was the middle size. There was a bigger size, which was in the US.
Oh, yes.
And what's the volume of the bigger size, and how much plastic can go into it?
This one is about 1 kg of plastic. It's about 15 centimeters. The largest we've done is 25 centimeters tall. It's 15 centimeters in diameter, and it has a part weight of 4 kg.
And you said that the smallest one, when you were doing your presentation, it was 10 seconds.
It's about, yeah,
you said 10 seconds on the build, 15 seconds?
Yeah, 15
and
seconds.
How many of the mid-sized ones? You said 3 on a build plate?
I wouldn't consider this to be mid-sized. This is
This is
mid-sized,
mid.
and
Okay.
you can fit. I think it's 12 on a build plane with this size.
Okay.
Looking very much forward to seeing this one come out. That's also about the biggest we can do on the Cars Buffet without the injection mold machine stressing out. So if any of you know somebody with a large molten unit, well, get in touch.
and the cross buffet was a 500 ton, you said?
It's a 50 ton only.
50
It's a
ton.
50 ton with a 32 millimeter screw, so it has a shot size of approximately 70 gram.
Okay.
Yeah.
A question came about the price of these resins. Can you give a range of these
The range
materials?
is between 200 and 250 US dollars a kg if you buy 1 kg bottles, and then of course we offer volume discounts if you buy larger quantities at the same time.
Here's a question about, in general, how can people purchase this and get support and so on. Maybe I asked that question to Michele. Michele, are you on the line?
Yes, hello everybody.
Okay, awesome. So Michele, maybe a quick introduction about yourself and something about Nexa, and what's the arrangement between the partnership in terms of the commercial arrangement? How can folks access the system? How is the support managed, and what's the plans as of now?
Okay, well, briefly, I'm the Chief Growth Officer for Nexa3D. I'm delighted to be here. I'm delighted and proud that basically Nexa is empowering Addifab to create unseen parts. It's just amazing, and basically breaking the boundaries of injection molding in a way that parts can be produced that in the past were or with different technologies were not possible. The long shot here is that as Lasse has already anticipated, Addifab will do all the due diligence in order to help potential customers to explore the application, and then they also basically will supply the full process to customers. Nexa will not only provide the printers to make this happen, but we will provide our support through our network of resellers for installation, training, and support. So leads can go either directly to us or to Addifab. Then, and Sean, you're not totally innocent on that because you will coordinate that obviously with Addifab. We'll go through the full analysis of the flow, and then we will support, as I said, with Addifab providing the full system and us supporting the application.
Awesome. Thank you, Michele. So any questions for Michele, please put it in the chat. Hey, Lassie, so could you walk through the process? This is not a question, but I think it's important to clarify. If you have a customer, they have a CAD file of a part, typically. So there's some designer in a cosmetic company or whatever, and they say, hey, I think I need to make this polypropylene part. And they've got a drawing or a CAD file. They send it to you. Can you walk through what happens with some real life experiences you had, and then relate that to the classic way of doing things, right? So cut a tool, and so what you do, which is different than the classic way, what's the time advantage, cost advantage? What's your experience in those situations? So if we have customers on this call or people who say, hey, you know, I think I can use this technology, what is my first step? So I'm trying to imagine that, and then what exactly would you do?
Okay. So what customers usually do the first time they want to start working with freeform injection molding is to reach out to Addifab or one of those customers we have who are running as a service manufacturing. The starting point for Addifab is always the CAD file of the part itself. And what we do with that part, of course, depends on the design of the part, but most often we will wrap a tool around it, which means that we turn the part into a cavity, a negative, and then we basically add a block of material around it. Now, That allows us to do simple one-off prototypes. When we want to start doing slightly more, well, let's call it realistic tooling, we start working split lines, also to allow the manufacturing of tools that can be taken either fully or partially apart. And once we have devised a tool design that we believe in, we run it through a mold flow simulation to make sure that we haven't skipped anything important. And then we basically start printing. Depending on part size and precision requirements, we have a couple of different printers to use. I mean, for high throughput applications, now it's going to be the Nexa in charge. For high precision, small parts, we may be using the Addifab printer. But the key objective is to get to printed cavities that are useful with injection mold machines as quickly and cheaply as possible. Once we have printed the cavities and assembled them if need be, we then walk into the injection molding domain. I'll try to see if I can get a bit closer to the injection molder here. So now I'm going to try anyway with my laptop. So what we see here is basically a tool frame. In this case, it's an allo block, and this is what allows us to inject the heated material into the 3D printed tools without the tools collapsing. Once I have my tool frame set up in the injection mold machine, I will insert the tool like this. And then the next step, let's see how that goes with the is to press the go. And now what the injection mold does is pretty much what any injection mold does. It squirts material into the cavity. Now, keep in mind that this injection mold machine has been sitting idle for 40 minutes now while I've been talking. So I'm not entirely sure what comes out of this shot. Normally, we do a cycle time of 30 seconds between shots. But let's see what happens. Okay. And this is one of the unique properties of freeform injection molding. The frame is, of course, a bit of a tight fit. But since the mold is an excellent insulator, I'll just leave it here because otherwise I'll break my fingers. The tool is an excellent insulator, which means that the material that I've just injected stays warm for the entire injection cycle. And now the next step, I'll take one which I pre-cooked. The next step is to, of course, move this into the demolding tank to get the component out. And that's the process in a nutshell.
And so you could keep at your end, at the Addifab end of things, you could keep finding the right tool design with your software, test it on your injection system with the 3D printer and injection system, and then dissolve it and send it to a customer and say, hey, that's a CAD file you sent me. This is the best way you can produce this using our technology. And that's a little bit kind of what I would call the first cycle of contact between a customer's real project and then an evaluation that had you done it with a metal tooling, it would be 6 weeks, and here you do a little bit of an economic analysis as well as part of a repeat, right?
And then, of course, we need to discuss with the customer how to implement freeform injection molding, because some customers will want to access freeform injection molding as a service, basically. They do not have the space or the need for very short lead times, or they prefer to not invest in injection mold tooling and injection mold machines and printers. Another group of customers will want to implement this technology for their own use. And there we, of course, support with configuration management. We help customers evaluate their needs. Some will need big printers, some will need small printers, some will need a combination. We have several different use cases as in the R&D, in production and spare parts manufacturing. So we typically go through a fairly exhaustive analysis to determine what is the right implementation of freeform injection molding with you, dear customer. And then, of course, it's a matter, please, yes.
No, finish, because there's another question.
Yeah. And then, of course, it's a matter of getting the equipment installed with the Nexa equipment. As mentioned, Nexa will be supporting with the printers and everything associated with their implementation. Whereas Addifab will, of course, support with application-specific knowledge about how to run freeform injection molding for particular applications at the customer.
Another question about venting. Is there any special venting requirements for the resins other than what, while using it with the Nexa printer, any special cleaning, curing equipment beyond what comes with the Nexa package?
We would always recommend users to invest in a demolding station, because the demolding solvents we use for the dissolving of the printed tools is a pretty high pH alkaline solvent. For that reason, we usually recommend something that is ventilated. We have a couple of different variants in our product program, but you will get very far with the Nexa, plus the X-Wash, plus the X-Cure, plus whatever injection mold machines you can get your hands on. So from the Addifab point of view, the important thing to support is, of course, also the dissolving of the printed tools. And that's where we have some specialized equipment.
Okay. This is not a question, but maybe you could emphasize the resources available. I know you had it on one of your slides. So what's in Palo Alto? What can people do there? What's in where you are, Lasse, in terms of what capabilities you have there?
Yeah. In the Danish headquarters, we have a mold lab with quite a lot of, well, we've got some pretty experienced CNC machining, or maybe not even CNC, a 50-ton, a couple of smaller injection molders, and then in the room next to me, we've got the 3D printer sitting, but you already know what they look like. In the Palo Alto office, we will have a desktop configuration of the freeform injection molding production cell, which we have developed to accommodate affordability requirements and requirements for R&D staff. So that's with the compact footprint in mind. For that particular setup, we will also have a freestanding ventilation unit included to ensure that people can maintain a good working environment. And the Palo Alto setup will be primarily targeting R&D departments, small mid-sized companies wanting to get started with freeform injection molding with a high quality setup that does not require too much floor space.
And of course, Nexa have a large installation in Ventura with all kinds of support for our printers, with the ability to print, including all these resins as well. No more questions from the chat. Lasse, do you want to say any final words? Then I'll hand off to Michele to thank everybody, and then I will close the session.
No, I think for me it's important to thank everybody for showing up today. We will be hosting a couple of webinars following up on this one to demonstrate particular applications of freeform injection molding, and also to walk you through the mold generator. So from my point of view, it's important to say stay tuned, sign up for the newsletters we provide, make sure to visit addifab.com and Nexa3D, of course. I guess most of you already did that, otherwise you wouldn't be here. But thanks a lot for taking the time to participate in this webinar.
Thank you. Michele?
Well, thanks everybody again for being on this call. Please let us know if you have any other question. Please contact us. Lasse, Sean, and myself will be happy to guide you through this amazing application and make sure that you can enjoy this absolutely awesome technology that empowers you to do impossible things. Thanks again.